Hola amigos! Today I'm bringing you some fun VFX done using a skeletal mesh character and Niagara. The following 6 mini tutorials will explain a bunch of different techniques and will hopefully give you lots of ideas to create your own amazing art, but they are not going to be a step-by-step guide. This time, I will assume that you have some experience using Niagara and will shorten things a bit by just explaining the most interesting parts of each effect. However, if you still have questions by the end of this video, feel free to post a comment below and I'll do my best to address it. All of these effects are fine to use on 1 or 2 characters in runtime, but as you can see from the frame rate counter, this one is the exception, and I would only recommend using this many particles in something like a cutscene. It still looks great in slow motion though. It reminds me a bit of those Sony ads where they drop tons of bouncy balls down Lombard Street. Before someone notices the similarities and asks about it in the comments, yes, the idea to have multiple dance styles to show off these effects was partially inspired by a promo reel made by Method Studios using Houdini. I wanted to see if it was possible to recreate some of the effects in runtime, while at the same time explaining how sampling skeletal meshes in Niagara works. In any case, that is a phenomenal video and you should check it out. I'll make sure there's a link in the description below. Also, you will notice that I'm not gonna talk about painting on meshes, which was shown on the teaser video for this one. Don't worry though, I'm planning a more comprehensive tutorial about that topic, so I decided to focus today's video only on the more fun looking effects. And with the introduction out of the way, let's take a look at the setup that I'm gonna use for all of this. Here I have a very simple scene made using the meshes from the showcase examples and a controllable pawn, which is just calling a couple functions for each different key press. The first one of these functions sets the visibility of the skeletal mesh, then spawns the specified Niagara system attached to it, and finally sets the component to cast shadows, which is turned off by default. Spawning the system attached is important. It will make it so we don't have to feed Niagara a reference to the mesh later on and make sampling it a bit easier. Then the logic waits a moment before calling the second function, which simply toggles a different boolean value based on the dance type. And at this moment, anyone who knows about animation blueprints is probably laughing at me, and it would be right to do so. This is no way to set up a character's animation space or logic, I know, but please be indulgent. This is just to showcase the effects. Of course I would never make something this bad for an actual project. Or would I? Let's take a look at the Niagara editor and check out the first of these effects. This one is quite simple. I'm just spawning a bunch of spheres all over this mesh and keeping them attached until half of their total lifetime. After that, the regular physics solver takes over and sends the particles flying with any velocity that the mesh had at that point. This emitter is a GPU sim with fixed bounds that only loops once. I use the fountain template, but then remove most of the original modules anyway. It spawns 500 particles all at once and then gives them a random lifetime and also a random color. The initialize particle module also sets the mesh scale to a random uniform value. A key aspect of this effect are the initialize and update mesh reproduction sprite modules. These are relatively new to Unreal and provide a quick and easy way to sample a skeletal mesh without having to handle all the parameter outputs manually. To make them work, you will need to add both of them, initialize in the particle spawn stage and the other one in the particle update stage. Let's take a look at the module's parameters. The first section is used to select a mesh. You can either specify it as a parameter or directly sample whatever skeletal mesh the system is attached to. If nothing else is selected, the preview mesh will be shown. The sampling regions and skeleton options allow you to specify which part of the mesh will be sampled. This can be useful if you want to emit particles only for certain areas of the model, for example to show damage or other similar effects. You can ignore the rest of its parameters for now, except for the Override Intrinsic Parameters checkbox. When activated, the outputs of this module will be directly applied to the particles. Otherwise, they will just be output variables and will be up to us to use them. For this example, we'll change this value in the update module. Here, I have set the property to be a bool by float comparison. The value will be true for half of each particle's lifespan, attaching them to the mesh. Afterwards, the sampling output won't be used on that particle, essentially freeing them to the physics solver. The rest is just your regular gravity, drag, and collision modules, which only affect the particles once they are detached from the mesh. The material on this is also very simple, just the particle color passed to the available fuzzy shading material function, and also adding a bit of emissive Fresnel to highlight the edges of each sphere. Before we move on to the next effect, let's summarize this system. First, I spawn the particles on top of the mesh and use the randomly assigned lifespan to determine when to stop following their assigned triangle. In the next one, I'll introduce two changes. First, using the sample UV information to paint each sprite, effectively making a copy of the mesh out of particles. Next, setting their lifespan using an expression to make this fake mesh dissolve from top to bottom. I think I didn't set the UV scale correctly on this one, so the texture on each sprite is a bit off, but you get the general idea. The skeletal sampler is also getting the normal at each point and applying it as the sprite facing property, so they are even aligned with the mesh. The sprite material is even simpler than the previous one. Let's take a quick look at it. I made an exact copy of the material that the original mesh was using, but I added this function called Niagara_mesh reproduction sprite UVs. This function will get some of the sample values as a dynamic parameter and calculate the UV that each particle is sampling from. We can then simply pass its outputs to each one of the texture samplers, and the particles will map the textures at those coordinates. For a simple effect like this function and modules are the easier way to go. And back on the system overview, the bool by float comparison is the same, except I'm using a different value to enable physics after 70% of the lifespan has passed. The change here is how I'm setting that lifespan on each particle. Since our mesh default pose is upright, we can map the particle's life to a value based on their vertical coordinates when they spawn. This code is 1 minus the vertical coordinate divided by the approximate height of the model, and then multiplied by the maximum time you want the particles to live. I added some extra height to extend this time a bit, but note that this is a lot of eyeballing to get the timing correct. If you have to be precise, you could calculate the bounding box of the model and also include a speed factor in this code. The rest is pretty much the same as in the previous effect, except that I added a curl noise force and increased the drag to give the final effect a bit more of a turning into sand look. Using this as a base, if you tweak the parameters a bit, added some noise to the lifespan, and changed the color over time, you could make something like the Thanos snap VFX in your game. Like I mentioned earlier, in this one I went a bit overkill with the number of particles, but I wanted to show how to manually use the sample values from the module. First, I created a new float variable for each particle called convergence. This is mapped taking a random value from a curve, which is a very useful way to make a biased random selection, rather than an uniformly distributed one. In this case, the idea is to have only a few particles follow the mesh closely and then have the rest be a trail of progressively smaller ones that loosely track the mesh position. This same property is then used in the initialize particle module to choose its color and set the mesh scale, in both cases using curves to control the gradients. Here I'm using the same bool by float comparison again, but you will notice that this is set to a tiny 0.1 value. This was just to give the particles a moment to show the mesh shape before they started to go too crazy. The main part of the particle's behavior is set manually. For position, I'm using a smooth lerp over time to move the particles between their current position and the sample value on the mesh. using the convergence property as alpha. For velocity, just applying a small part of the sample value from the mesh. Since the convergence property is so small for some particles, even light curl noise forces have a big impact on those, allowing for some interesting and colorful effects to happen. The next example uses a different module, which we could call the advanced version of the mesh reproduction sprite. Sample skeletal mesh does basically the same as the other one, and even gives you more data about the mesh. However, it has no complementary modules, and it's up to you to use the sample information which is available as module outputs. To make these spinning metal scale looking things, I'm using two of the outputs available. First, the sample position is directly applied as particles position. Next, I'm using an update mesh orientation module to make the long part of the mesh face the sample normal direction. A second mesh orientation module adds a rotation rate driven by a curve with a sharp transition at 0.2. Note that since I'm using the normalized looped edge of the emitter as the curve index, that was the setup I needed in my case to get a perfect 180 rotation each cycle, with enough time between changes to make it look more distinctive. If you're making this effect, you will probably have to tweak these numbers and curves to adjust to your own timing. The last part is setting the color of the particles based on the mesh orientation. This is what makes the scales change color depending on whether they are facing up or down. This color is then fed to a material which is simply a metallic surface shader, using it as a base color. And with that, we are past halfway in this video. The last two effects will be using ribbon renderers and have a slightly different setup than all the previous ones. This first effect is only visible while in motion, so let me bring the footage of it again before we go back to the Niagara editor. This one uses two emitters, a first one sampling the skeletal mesh at a few positions, and a second one that uses a particle attribute reader to spawn the ribbons from it. A scratchpad module is then used to give each ribbon a random color. And this is the setup. An important detail to note is that the source emitter needs to have the requires persistent IDs property turned on. These same IDs will be the ones used to assign ribbons to each particle on the second emitter. The first emitter should be pretty familiar by this point. It's very similar to the second example, but it only emits 100 particles and doesn't have a renderer. The second one uses the spawn particles from other emitter module, which is a very convenient way to avoid managing a particle attribute reader from scratch. I recommend to check the calculate spawn rate per particle option, otherwise things could easily get out of control. In the initialize particle module, the lifetime basically controls the length of the ribbons, and using a curve to set the ribbon width was silly because it doesn't really affect particles on spawn. I forgot to remove the curve, but I'm using a scale ribbon width below to achieve the intended result. The sample particles from other emitter module can get a lot of information about the other emitter, but we just need two things here. First, the position of the other particles, and second, their ID, which conveniently the module has already an option to apply to the ribbon ID property. Let's take a look at this scratchpad next. You could do this in a single line of code in a custom expression, but I thought this was a nice way to show it. What I'm doing here is taking the ribbon ID, which the other module already has assigned, taking the index and outputting that after dividing it by the number of ribbons, which in this case is 100. This is just to convert the ribbon ID from a Niagara specific type to a 0 to 1 float value that is much easier to use in other modules. In this case, I'm assigning a random color from this gradient based on this value to have it be consistent for each ribbon. If you wanted rainbow multicolored ribbons, this wouldn't be necessary, but either way, this is a nice way to filter the particles that belong to the same ribbon, which can be useful for many other effects. The reason I set the number of source particle to 100 is that higher values quickly overflow the maximum persistent IDs that a single emitter can handle, as we can see here if I set the spawn number to 500. This overflow on the particle IDs causes them to bunch on the system's origin, which, I don't know, could be an interesting effect on its own, but not really what we're looking for today. There are a couple solutions for this problem. The first one is more complicated to set up but more efficient, and it is to set the particle effect IDs manually as a separate property on spawn. Doing this, you could increase the number of source particles that your effect can handle, and in more serious projects would be the way to go. For this example though, I'll keep things a bit easier by showing you the easy method. This one is not as scalable, but if you only need a few more ribbons and you don't have many instances of this effect, should work in most situations. This one was done by combining 4 copies of the same effect with slightly different parameters. The main differences between each one of these and the previous effect is that these ones start with an initial velocity based on the phasing orientation of the source particle to get them going without the character moving. They are also affected by gravity and have a small curl noise force. Each one has also a slightly different scale and color settings to get some extra variation. Like I just mentioned, you could also make this effect by having one or multiple emitters sample from the same source one using a particle attribute reader, and then use that information to fabricate and assign your own ribbon IDs to each new particle. However, I've been kinda sick this week and already feel like I'm losing my voice, so the step-by-step guide for that will have to wait for another day. This material is very simple and similar to the one I used for the first effect. One of the differences is that you have to make sure that the Use with Niagara Ribbons option is checked on the material properties. Other than that, the changes are mostly to make it look a bit more solid and rubbery. And that's all for today. I hope you enjoyed these mini tutorials. Post a comment below if you use any of these effects or anything inspired by them in your own projects. If you stayed until the end, thank you for watching this video. Give it a like and consider subscribing if you like this content and want to see more like it. See you next time.